The Arctic fox is a small fox which lives in the Arctic regions of the Northern Hemisphere, which consists of the tundra biome, characterized by snow, extreme cold, and harsh climatic conditions. The main challenges that the Arctic fox faces is the extreme cold. And so some of the adaptations they have to retain body heat and endure starvation include thick fur for insulation, the ability to reduce their basal metabolic rate, and short limbs to decrease their surface area to volume ratio. As I said before, the main challenge they face is maintaining body heat in the extreme cold. The Arctic fox stands on ice and snow surfaces which are below freezing and below their critical thermal minimum of -7 degrees Celsius. So how can they maintain their body heat when they're in such cold? So Arctic foxes are endotherms, meaning they use internal processes to create and maintain heat. And in their case, they use countercurrent heat exchange in their paws to keep their tissues above freezing, their warm blood circulating, and this helps keep them mobile in the extreme cold and allows them to hunt for food and move around. So how does countercurrent heat exchange work? The proximity of arteries and veins in the paws, as you can see in the diagram, allows for heat exchange. So warm blood flows down, and as it nears the pad of their paw, which is in contact with the ice, it cools down. And so you have cold blood flowing back up. However, since they're close together, the cold blood is heated up by the warm blood flowing down. And other foxes, such as the red fox, do not demonstrate this mechanism in their paws. So they would not be able to stand on the ice or cold surfaces for long periods before reaching their critical thermal minimum. And so to explore this adaptation further, I'm posing the question, how will vasoconstriction affect the countercurrent heat exchange in the paws of an Arctic fox? So mammals use another mechanism called vasoconstriction, which is the narrowing of their blood vessels to maintain core warmth. And this also results in an increase in blood pressure, so more blood will move faster. Thus, the blood in the Arctic fox's paw will spend less time exposed to cold and more time in circulation throughout the body, allowing countercurrent heat exchange to be more effective and efficient. Thus, I hypothesize that vasoconstriction will enhance the conservation of heat in the blood, and as a result, improve the ability of countercurrent heat exchange to maintain heat in the blood. And so in my experiment, I will take foxes from 4 different experimental groups, and I will have them stand on ice in a simulated tundra environment and measure their core body temperature over time. And my independent variable will be blood pressure, and I will change that via vasoconstriction, inducing vasoconstriction and vasodilation. And my dependent variable will be core body temperature over time. And so my positive control and experimental group will be the vasopressin injected foxes, and vasopressin is a hormone which induces vasoconstriction. And I'll be comparing that to the negative control group. So we have hydralazine injected foxes. Hydralazine induces vasodilation. And for the hydralazine injected foxes, we should see a decrease in core body temperature. And then for the saline injected foxes and the non-injected foxes, we should see the foxes just maintaining a constant core body temperature, since their ability of countercurrent heat exchange should not be affected. And in the vasopressin injected foxes, we should see an increase in core body temperature. And I have some constants to reduce variance. So the time spent on the ice, the time intervals when their body temperature is taken, and the amount of vasopressin or hydralazine injected per fox. And if my hypothesis is true, the core body temperature of foxes injected with vasopressin will increase due to the increase of warm blood in circulation, proving that there's a positive correlation between vasoconstriction and effectiveness of countercurrent heat exchange. And if my hypothesis is not true, we should see that the core body temperature of foxes injected with vasopressin will remain constant or decrease, indicating no correlation between vasoconstriction or a negative correlation between vasoconstriction and effectiveness of countercurrent heat exchange. And we can also see, if my hypothesis is not true, that the core body temperature of foxes injected with hydralazine will increase, and more research should be conducted to study the relationship between vasodilation and countercurrent heat exchange. And lastly, my statement of ethics: to reduce and prevent harm to the foxes, I will be closely monitoring them in a controlled lab setting and minimize contact with them and handle them gently. In addition, their paws will be exposed to more moderate cool temperatures, not the most extreme cold, to minimize the risk of the fox reaching their critical thermal minimum. Thank you.